was about her, mostly about her research. And so I'm really looking forward to it.
Thank you,
And
Francesca.
yes.
Yeah, thank you, Francesca. Okay. The last part of our 4-part journey together. Today is almost not at all pedagogical. That is to say, I'm not going to make you do anything. I'm not going to ask you to do anything. I'm just going to talk about what excites me. Okay? So you can maybe sleep, but I encourage you to interrupt me at various points because I'm talking about a lot of different things. And if you wait to the end of the talk, we would have talked about 5 completely different things in between, and the conversation might not go so well. So be sure to interrupt me as we go along today. Okay. What I wanted to do today is start with a little philosophizing, then pick out a few papers from the 90s and the early 2000s that I think everybody should read and that nucleated a lot of work in active matter. Then very quickly, within 5 minutes or so, I'll transition into my story. This will all be work that we are doing, myself and my collaborators. And so it's not going to be very universally appealing. And then I'll speculate about the future as to what else remains to be done from my perspective. So let's start with some philosophizing. This is a statement that I use a lot when I'm trying to read science papers, where when I say knowable facts, so the things that I will not dispute in any paper that I'm reading. Because this, yes, this much I agree. And then there are some stories following that I don't agree, I don't understand or don't agree with. It's good to demarcate that line whenever we are reading papers, because you have to think of the words on the paper from the context of the person who wrote it, and our context is typically different. So I wanted to give an example from history to illustrate this point. I have lived in 2 countries, about half and half in my life. One is India and the other is the United States. And both of those countries have a history that has 2 versions for every story. Right? There is the version of one half of the population that experienced the same third-person facts but had a different interpretation for it, and then another half who have a different interpretation for it. I'm sure this is true for Brazil too. If history is a good example, where there are the same third-person facts result in 2 different stories. That happens a lot in science also. And the beauty of science is that we can figure out what the third-person facts are and proceed on that. Neglect the interpretation, what is your intention, what is my goal, and stories like that. Right? So take that perspective with respect to the things that I will say here. So when I say the history of active matter, it's really a history as viewed by me. So there are many different histories for active matter that can be written. I have written 3 different versions. This is today's version. So I want to start in the 90s. The first thing that set off this whole process of starting to think about collective dynamics of individually propelled agents started with microorganisms. In the 80s, people started thinking about microorganisms and collective behavior in microorganisms. And this paper by Pedley and Kessler, which is a review in journal, annual reviews of fluid mechanics, lays out the basic model that then everybody borrowed, and microswimmers and suspensions of microswimmers became a thing. So that's one of the starting points. And around the same time, people figured out how to make microtubules and motor proteins and things like that. Purified components work in vitro. This is one of the first papers that uses kinesin and microtubules and stuff like that in the context in which we would like to think about it, as materials, not inside some complicated cell which is doing some magical thing, right? And around the same time as these 2 innovations were happening, the StatMech people got in the game. We got 2 papers. 1995 is like the year of Einstein. It's like the year of active matter. We got both Vichek and Toner at the same time. And so 1995 became the year of active matter. A whole bunch of things happened, and everybody started doing a lot of things, right? And then I rapidly fast forward to the 2000s, and the way I think about revolutionary things that happened in the 2000s was we got synthetic active matter. This is the first paper about catalytic self-propulsion from the Ayushman Sen and others. And this was quickly adapted. We made lots of colloidal particles that could be self-propelled with catalytic interactions. So synthetic active matter got started. And simulations of active matter really took off around the time this paper came out. I couldn't quite find which was the first paper in this oeuvre, but just hard particles or WCA particles or spring repulsion particles with self-propulsion on them or some other version of activity on them and look at their collective behavior. It got started around 2006. And of course, the other thing that happened at this time was the generic instability. The Ramaswamy papers and the Giovanni papers that told us how to think about suspensions. Once these framework objects were set in place, all the things that you've heard about in this summer, in this school, happened. All the things that Julia spoke about, all the things that Rodrigo spoke about, Francesco spoke about, and I speak about, all of that happened building on these foundational papers. Now, that's all I'm going to say about the history. This is just my, the one lens version of the history. There can be many different versions of the history of active matter. Now I want to change tacks and talk about one story that's ongoing in my life right now. And that story was hatched with these three people. So the four of us got together in the winter of 2018. We were very frustrated with ourselves because there was way too many things happening in soft matter and active matter, and we didn't know. It was like we were paralyzed in terms of what should we do. There are too many things to do and so much problems. You know, you have your hair on fire feeling sometimes. You see 6 papers on archive, all of which you absolutely have to read in order to be able to finish your writing whatever paper you have to read. That kind of hair on fire situation. We got together and we said, okay, what shall we do? We decided that what we will do is the four of us will craft a long-term goal for ourselves, and in the local when we were taking steps, we will random walk, but with a bias towards our overall goal. That gave us some peace. That even though we got kicked to the left, no, there's some theta component in the direction I'm going, it's okay. That kind of thing. So we were looking for a big picture goal of what we wanted to do. So the four of us made this plan. And subsequently in 2020, we got another team member, Guillaume Duclos, who's also joined us in this endeavor, though we are keeping our distance from him still because he's not tenured. He'll get tenured this year. Then we will start using him more. Because in the US, you can't get tenured if you don't have papers with you alone on it. That is, you can't have a bunch of other professors on it. They don't like that. So anyway, so these four people are the people that I work with. Mike Hagen is a theorist, and Seth, Dwanimir, and Guillaume are all experimentalists. And the story we set for ourselves was we looked at these movies, and we said, okay, what I'm looking at here is some spatio-temporal organization of material and forces in such a way that I'm getting function. The function in the first movie is flow. I get coherent flow on the scale of my system. The function in the second movie is motility. The function in the third movie is assembly and disassembly and transport. And the way that these functions are accomplished is by the actin microtubule sector of the cytoskeleton of a cell. So actin and microtubules are polymerized versions of two particular proteins. Associated with them, there are hundreds or thousands of proteins, hundreds up to thousands, we don't know how many, associated proteins and biochemical cycles in the cytoskeleton sector. And it's just this that is giving rise to all of these functions. And what we thought was, okay, there's force generation at the microscopic scale by the stepping of the motor proteins. Then there is organization and modulation of this stress in order to give rise to these functions. So let's build ourselves one of these. I want to build myself a bag of crap, which if I press a button, sets up circulating flows. If I press another button, it starts moving. I press yet another button, and it starts doing assembly, disassembly processes. Okay, that's our lofty goal. And because we were soft matter and statistical mechanics people, the way we formulated the starting point was to take a mechanical and statistical lens to what's happening here. So I want to motivate that by showing you this movie. This is also a movie of a crawling neutrophil. It's from the Betsig lab in Genelia Farms. And what you're seeing here is in purple, you're seeing actin. In green, you're seeing myosin. And you're basically tracking the cell, and you're imaging these two proteins, okay? And I think what you will agree with me when I say that that the top part of this, what is white? Green. This is green. Is that what you're seeing as white on the project? It's supposed to be green. It's myosin. So the green is myosin, and the purple is, or the magenta is actin. And you're not seeing anything else because those are the only ones that are labeled. And, oh, that's nice. There's probably myosin in the environment or something like that. There might even be stress fibers from some other cell that are corrupting the image. I don't know. This is just for inspiration because this is not my data. In the future movies, I will show you my data. There, if you ask me what is what, I will be able to tell you. This is, I just stole this movie from the bed. Nobel Prize winners don't annotate their movies. They just put it there, and then you have to figure it out. So, so the top, I think you'll agree with me that at the back, the cell is moving. The back end of the cell has large myosin activity, while the front end of the cell has weak myosin activity. The back end of the cell has some depolymerization and retraction forces with the focal adhesions, while the front end of the cell is just driven by membrane fluctuations and polymerization forces. And what, if I zoom way out and I don't want to think about all of the details of what's happening, the way I would imagine this would be that there is a contractile forcing at the back end of the cell that's pulling. There is extensional forcing at the front end of the cell that is pushing, and these two together result in the center of mass displacement of this guy. Okay? So if I take my StatMech lens to this, all I'm saying is I have the same microscopic ingredients. I just have myosin and actin, but they are spatiotemporally patterned in different ways, and that spatiotemporal pattern is adaptively and dynamically reorganizing to give rise to this function. Okay, supposing you believe that story, what we said was, okay, let's be Feynman. What I cannot create, I do not understand. These were the words on Feynman's last blackboard. Somebody took a picture of his blackboard after Feynman died. He died relatively young, so he was still in his office the day before. This is what he had written on it. So I like that. I never know anything till I do it. I feel the same way about math. I feel the same way about physics. I feel the same way about everything. So let's just do that. Let's create it and see if we can understand it. And the plan involved, let's make, let's measure, and let's control. Those were the 3 steps of the plan. And we started the making with something that we already had at that point, which is this basic motif of an active particle. These yellow things are microtubules. The green things are cross-linkers that basically bundle microtubules. They bring microtubules together and anti-parallelly align them. And the white things, do not, they are weak chemical bonds. They don't exert any forces. They just attach and detach, but they tend to attach long enough that the microtubules will end up aligning to each other. So it's a weak chemical bond. What I mean by weak chemical bond is that it's Van der Waalish. It's not so much that there is some molecular orbital thing happening there. And these white things are kinesin motor proteins that we had engineered at that point. These kinesin motor proteins are made by taking the brain of a freshly killed cow, blending it in a blender, and purifying just the kinesin motors. And then you take the kinesin motors and you engineer them. You put biotin streptavidin tags, make clusters, and purify them further, and then that's your myosin thing. This basic template of this biotin streptavidin tag, the PRC1, and the microtubules. If any of you have a microscopy set up in your university that has good micron resolution microscopy, and you know how to handle proteins, we'll ship you this basic template. We'll give you whatever you want. Because we have set up a factory. Because we are doing some data-driven thing, we have a factory. We have a procedure for producing it. So we'll ship some quantity of this to you. So if you want, you can email us, and we will ship you some things. And also, 1 to 2 students every semester come to Brandeis from various universities and get trained on either the proteins or the microscopy, namely what it is that you need to do. So if you or your students or anybody in your institution would want to pursue this kind of thing, email us. We'll tell you when we have a slot. You can come, you spend a month, you learn how to do these things. Okay. Now, so this is the basic template we started with. And, oh, there are labels. Okay, I forgot about that. And if I start with this basic template, just these 2 guys, then what happens is two microtubules come together. This is a time series snapshot. Time is going this way. Two microtubules come together and they stretch. So the motors push them apart like this. They start extending. They extend and extend and extend, and eventually the two guys fall apart. That's the basic activity of this system. Microtubules come together, extend, 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 fall apart. Then again, some other tubules come together, extend, 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 fall apart. That's the basic activity motif. And in terms of making, what the experimentalists have been doing, and I'll show you a bunch of movies along these lines, is making it more and more complicated. Introduce actin, introduce FD viruses, introduce liquid-liquid phase separation and motifs in there and things like that. I'll show you a bunch of movies about what the experimentalists are doing. But I'm a theorist, right? So I want to talk about what I have been doing in this game. So I want to talk about measurement and control. And for that, I'm going to stick to the 2D active pneumatic that Julia spent all her time telling you guys about, building the theory and stuff like that, because that's a well-understood, well-characterized system. We know how to do it experimentally. We know how to do it theoretically. We know how to simulate it. We know everything. So we want to play the measurement and control games in the context of this well-studied system before we go to all of this mess that those people are cooking up. Yes?
The microtools here, hello? Yeah. The microtools here, do they grow? Do you have dynamic instability?
No. These are all completely length stabilized. So we used to have Taxol length stabilized microtubules, but the tubulin did not like the Taxol stability. The sample did not live long enough, so now we have some GMCCP stabilization. So they are length stabilized. Nothing is growing. The only thing that's happening is moving. Density is fixed. Nobody is growing. Nobody's going in. Nobody's coming out. Okay. Now, what is the challenge with measurement? So let's say I want to measure some property of the system. What the experimentalists can give me is a movie such as this one. Will it play? Yeah, it's playing. It's some movie like this, and I have to do some analysis on this movie to produce these velocity fields, and those blue lines are disclination lines where the order is destroyed and things like that. I have to post-process this movie to extract this information before I can say anything about the physics of this system. And the challenges here are the following. First of all, I need to get good kinematic data. I need to robustly be able to get density and velocity from these movies that the experimentalists will be able to give me. And somehow from that data, I need to be able to back out mechanics. I need to understand what are the forces that are driving the system to have the particular dynamics that I am observing in my system. So that is the hard problem. And I can't stick stuff into the sample to measure it. As we already saw, active matter, the moment you introduce a boundary, changes around the boundary. So you're not actually measuring the properties of the active matter system far away from the boundary. Right? So I can't stick stuff in there quite easily. We are trying to figure out some stuff that we can stick, but it's generally hard. And even though at the single molecule level, I might know everything there is to know about kinesin, because at the single molecule level, you can use light as your clock and ruler. You can just use light to figure out the energetics and the forces and stuff like that of a single motor. Okay? But we are not interested in what a single motor is doing. We are interested in what happens on some mesoscale, some much longer length scale, where the single motor is less than a dot on this length scale. Right? There are millions of motors coming together to generate these kinds of motions. So knowing anything about a single motor does not give me relevant information for the dynamics of the material I'm trying to control. So given this challenge, we started a data-driven program where we wanted to take the movie and from that movie, try to measure whatever we can measure by using data-driven techniques. So before I launch into the data-driven techniques, because I'm going to be mostly analyzing this movie, I want to spend 5 minutes and recap the essential features of this movie that Julia already told you. I will tell you really quickly, just to remind you. The theoretical picture is that I have some elongated particle that's called the nematogen that has a force dipole on it. This thing is the force dipole. And they tend to align. There is a nematic aligning interactions because these are rods. I expect the dynamics of my system to be described by two variables, the nematic order parameter and the fluid velocity. I know the equations that these two quantities obey. We have tested these equations a lot with at the statistical level with the experiments. Everybody has done this because this active pneumatic is now exists in many labs, because anybody wants to come, we'll give it to you, you can go do your own experiments. So now it has been validated quite nicely in terms of what the properties are, and these equations are pretty good. And you have the usual things. You have the active stress, you have flow alignment and shear alignment and things like that. And you have the free energy, which is the Landau-Dijon free energy that Julia discussed in her first lecture, second lecture, I can't remember, one of the lectures, right? So that's, the theory is pretty well known at this point. And the basic phenomenology is also well known. Julia described this to you guys. Supposing I imagine that this is the pneumatic order in some domain I'm looking at, namely that all my rods are lined up in a straight line. Since they are force dipoles, all the forces inside that domain cancel, and the only force that is left is at the edge of the flat domain. And whatever the rest of the universe is that is holding the rest of the flat domain there will exert an equal and opposite force. So this is a mechanically force-balanced state for this system. But it's an unstable state, because the moment this guy bends a little bit, you can convince yourself very easily that this domain now exerts a force denoted by this red arrow on the rest of the universe. So the rest of the universe will clearly exert an equal and opposite force on it. So the green arrow force is going to make this bent domain move. So once it bends, it will move. And since you're pressing a floppy object into a wall, it will also buckle more. Right? Not only will the bent region start moving, it will also keep buckling more. And it will buckle and buckle and buckle until such time as you end up getting these topological defects. The defects appear because you can't bend a microtubule. You can bend collections of microtubules, but you can't bend one guy. It's too energetic. So you form defects. That's the basic phenomenology. And this basic phenomenology has been, so there is a conventional wisdom in this field. So we've been playing with these active pneumatics for 10, 12 years now since the first experiment, right? So a lot is known about it. A lot of people have contributed to our understanding of this system. So we know that the active stress is given by some constant alpha that multiplies my Q tensor. I know that the reaction stresses in my problem come from viscosity and pneumatic elasticity. I know that the only length scale that is relevant to the problem is square root of K over alpha, where this length scale sets the defect density, the vortex size, all of the other relevant length scales in the problem are proportional to this guy. And the only time scale in the problem is 1 over alpha. That controls the speed, it controls the velocity correlation time, and so on. So if you measure speed, you measure velocity correlation time, you measure whatever time quantity with units of time, it will all be proportional to 1 over alpha. So all of this we know. So what we said was, okay, step 1. Let's figure out what this alpha guy is as a function of the concentration of things you put inside the cup. So what you put inside the cup is microtubules, ATP, PRC1, the green stuff that bundles the microtubule, and KSA, which stands for the kinesin 401 motor, which is also the thing that drives my system. So what I want to do is I want to fix the microtubules, because we can't actually control for microtubule concentration that easily, because it's a sedimented system. Whatever sediments is what sediments. So keep microtubules fixed and look at what happens to this alpha guy as a function of the ATP concentration, the PRC1, and the KSA. This alpha is a theoretical quantity that has units of 1 over time. Yes?
You said the length is stabilized, but isn't length important for a correlation length?
It is important possibly, but these are 1 micron microtubules and the bundles are 100 microns long. So I really don't care about the length of 1 microtubule.
Okay, so there's
because these structures are hundreds of microns long, and each microtubule is 1 micron. So I really don't care if it's 1 or 10, it doesn't make much difference. It does matter, not all that much, and not for the data that I will show you here. Here, these are all length stabilized at the same point, so they have similar length distributions. Around 1 micron, with about 10% spread on good days and 20% spread on bad days. Other questions? Okay. This 1 over alpha guy, this alpha guy has some units of time. And I want to relate it to ATP concentration, which the experimentalist will tell me in millimolar, PRC1 concentration, which the experiment will tell me in some nanomolar, and things like that. I get some numbers from the experimentalist in terms of how much of this stuff they pipetted into the cup, right? And I want to use that number, and I want to use that data to figure out what alpha is, and I want to be able to do this repeatedly, so that I know that you should pipette this much amount of stuff into your cup, so that you will get defects that are spaced this way, and therefore I can control the material. Okay, that's my goal. Let's see how far we've gotten in this goal. One of the things that we did to try to get to this goal was to automate the process of trying to go from experimental movies to the information that I need to do any further analysis, which is what is the nematic director and what is the velocity in every region in my sample as a function of time, right? And initially, we had done what one conventionally does in these problems, where one looks at the, has pole scope data that tells me, because this is a liquid crystal, the pole scope data will be very bright if the liquid crystal is oriented this way, and very dark if it's oriented that way. So you can take gradients in intensity to figure out where the director is. That's what we used to do. But it's very expensive, very slow, and for every data set, it takes 2 days to get to Q and V fields. Okay? And so what we did was we said, okay, let's build a machine learning scheme that will basically do this much faster, and I don't have to fine-tune my machine learning thing every time I have to do this. I just give it data and it figures it out, right? So I want to make a couple of comments about machine learning that are big picture and not, that are not going into the nitty-gritty details of machine learning, but just to get a sense of context. How many of you already know how machine learning works? Good. So most of you know. So this big picture comment is enough for what I want to talk about. There are 2 views that you can take to any machine learning challenge that you set yourself. One view is the linear regression view. In this view, you can think of the problem as follows. What I have in my movies, let's say, is some I intensity of my, it's a bright field image. So there'll be some intensity that I can see in my thing. That will be as a function of what pixel I'm looking at. Let's call it X. Let's just pretend it's 1D at a time T. So I will have some data set that goes from X0, I of X1T, whatever how many ever pixels I have in my video frame, in one frame, right? And what I want, the problem I'm trying to solve is I want to say that at time t plus 1, I want to know what this intensity would be at time t plus 1, given the intensity at time t. Okay? And if my frame rate is fine enough, I expect that whatever is happening, I'll get some matrix that describes this relationship. And because we are doing what is effectively a fluid, clearly an I over here cannot care about an I all the way over there. So this matrix is going to be sparse. Yes? Because there'll be local blocks of things talking to each other, but there'll be no crosstalk from all the way here to all the way there. Right? Okay. Now, once I formulate my problem as a sparse regression, this is just a sparse regression problem. All I'm doing is, I'm doing linear regression. I'm trying to fit a straight line between 2 points in data, whatever a straight line is in these dimensions. And I just want it to be, I know that it is sparse. I know that whatever I'm trying to fit is a sparse matrix. Right? Once I formulate the problem this way, then it's straightforward, because the applied mathematicians have given us a sequence of tools that go by various acronyms, PCA, POM, and various, there are many, many acronyms like this. PCA stands for Principal Component Analysis, and so on. And all of these acronyms give us techniques for how to solve for this matrix. And they also have been implemented in a massively parallel scheme using neural networks. The using of the neural network is nothing fancy. It's just a massively parallel scheme to solve my sparse regression problem. Okay? So you can find a sparse regression scheme that will work for your particular data and use it to generate this matrix between frames. Right? Then once it understands, and of course this matrix sparsity changes depending on the separation between frames. If I try to take a t plus 5 frame and compare it to a t frame, I actually need a lot less information here than I imagine because of the fact that it's a hydrodynamic thing. It's not going to be all that correlated far away. Okay? So the sparsity changes as you change your window, and you can use appropriate schemes to try to figure out how to construct this matrix. Okay? So that's step one. Then the step two is once I know intensity as a function of, I know the machine learning scheme has learned how to, given intensity now, predict the intensity that will be there in the next frame. I can ask it to tell me the director by taking gradients of this intensity. If I take gradients of this intensity, the director will be orthogonal to this. So I need the direction that is perpendicular to the principal component of this gradient of the intensity. So from here, I can ask it to tell me what the director is. Okay? And so the first paper here basically it tells you how we did this. You see all of the co-conspirators on the paper. And it's much better to do these kinds of schemes with a physics goal in mind and physics knowledge in mind. Because one of the things that we found when we did this work is that the data gets crappy the closer you get to the defect core. Wherever there is a defect, the data gets crappy because the director is fluctuating too much. So then we know that. But if we gave it a movie just like that, it would produce very bad fields. We produced very bad fields for a while, and then we realized, oh, we should mask the data wherever the S is low. So then what we did was we took the data, we binarized it into zeros and ones, and we blocked the zeros where the cores were, right? And then it started producing much better fields, and now we have a scheme that is quite robust. Literally, you give it data that was done with a different concentration, different physical conditions, different effective dynamics, it still figures out what the director field is. So, okay, I'll keep going. I have another pitch for machine learning, another way of thinking about machine learning that is in terms of Bayesian probabilities. But if we have time, we'll come back to it. And similarly, this Bayesian probability scheme is basically is a better picture to understand the optical flow scheme that we used in the second paper for producing the flow velocity. But we cheated a little bit. We went to Google Brain and got their traffic model. They have an optical flow traffic model that they use data from traffic signal cameras to build the flow of traffic so that that's how your Google map knows where the red lines are and how long the red lines extend. The AI calculates how long the red line extends. So we took that model and then took it apart a little bit and customized it for our own purpose. So we did not build it from scratch. We built the first one from scratch, second one we cheated. Because at this point we understood enough machine learning that we could go steal from other people. First problem, I didn't know any machine learning, right? So I had to build it. Right, okay. So then we built these two. So now I have a scheme where I can give it data and it will produce Q and flow fields. Now, second step. So I can take a movie like this and overlay it with the blue arrows are the flow velocity that the optical flow is spitting out. Second step, now I want to use the data to find model and parameters. What do I mean by that? I mean, let's take the data. I have measured Q and V using whatever machine learning magic that was there on the previous slide. And what you do is you construct the most general model that you want to consider. Keep as many terms as you like. You think it should be a PDE, maybe there should be quadratic nonlinearities, maybe there should be cubic nonlinearities, maybe there should be 2 gradients, maybe there should be 3 gradients, maybe there should be cross terms, whatever. Just build a library of every term that you can imagine, okay? Then use the data to calculate both the left-hand side and the right-hand side from the data. Then again do sparse regression to find the coefficients. So that's the technique for trying to identify the dynamics. And this technique is invented by all of the applied mathematicians. I cite the papers here. Mike and I heard about this at a conference in 2019, pretty much as soon as we started this project. So we were all excited. Yes, yes, let's build Cindy and let's figure out what alpha is and so on. So that's what we did. So let me illustrate a little bit more what it is that we did. So I have, let's take an equation like this. I have some equation for qxx, and it is a sum of, let's say, 30 terms. Each term is some fi of q and u. It's u dot grad q. It is u dot grad q square. It is q grad q, things like that. Let's take 30 terms. And do this fitting, linear regression, sparse linear regression, or ridge regression, though right now we do lasso, to fit the parameters, and ask, does the fit get, so the thing on this axis is the error, and this is the number of terms, right? And you see that the error stays small. You can drop terms, drop terms, drop terms, and at some point is where the error jumps, right? And so we say, okay, wherever the error jumps is the model. Okay? This is very stupid, but this is what we did in this work. Yes?
Yes. How do you choose which are the, I don't know, 5 terms that are keeping?
Oh, so
Or you have to
we
make
look at
all
the
possible
size of the coefficient and size of the term. So you can look at the column vector and ask what is the size of the column vector associated with that term. If it's a very small number compared to the actual value of q, that will be a less important term.
Okay, so you start with many terms and you start
Dropping them.
Dropping the less important.
Yes. Numerically, number-wise smaller terms, you drop them.
Is it, there are no hysteresis or something that if you erase in another order, you're sure you get to the same terms?
Yeah, so there are all these problems, and people have come up with ways to do the Cindy scheme better, where all of this arbitrariness of what I'm saying here does not happen, right? I don't understand those schemes yet, so it is being, my postdoc claims he understands it, so I told him, okay, you understand, you do it. Well, let me understand. When I understand, I will come and look at what you're doing. So I haven't understood it yet, but people have figured out schemes where you drop randomly. And you build a convergence matrix and ask, okay, now what is, irrespective of the direction you come, are you converging to the same point? That's the basic idea, but this numerical implementation, I don't understand what they're doing. So ask me in 2-3 months.
If all the remaining parameters, 10 or the 9 remaining parameters were still important, then deleting them wouldn't also imply big changes in the quality?
Somehow it didn't for this particular equation, but generally it does. There are huge jumps in errors once you go below the ideal model.
So I guess, and a second question. So continuing what Rodrigo was saying, if I put that parameter 10, now I keep it in my list, but I continue deleting 9, 8, 7, maybe it's only 10 the important one, and even the other ones are
possible. That's why we continued to drop to see how the error changes.
But you've already dropped 10.
Right? Until I dropped 10, the error didn't change much, and then it jumped, the error jumped a lot. And I don't want to live in a 1 minus r square regime where my error is almost 50%.
Okay, yeah, we can talk later, but
yeah,
the idea is
5 parameters, but with 10 on it, that you might get a small error.
Yeah, what I'm saying is that you don't delete 10 because you know it makes a big difference, but now you delete 9.
You're saying
8,
keep this term,
keep 10,
start
exactly.
dropping other terms while keeping this term.
Yeah.
Yeah,
So
which is, this is the multi-directional convergence scheme. This was just for me to learn how to do this. So I did it in a context where I knew what the answer was going to be, right? So I didn't do all of this fanciness here. I was just trying to validate the method. But all of the fanciness is being implemented right now, and I don't understand it. It takes me a few weeks or months after my postdoc says, oh, I can do it, for me to understand what they are doing. So it's slow. I don't like this stuff, but okay. Okay, now, wait, is that all? Oh, I wanted to show you one more thing. I didn't put that slide in. If you go and look at what these terms are, they are exactly the terms that you need for Galilean invariance with the appropriate 1 and -1 signs. It has this exactly the viscous stress term that you need with 1 in front of it. Everything comes out to be 1. It's miraculous how close to 1 those numbers are, 0.99 and stuff like that. I somehow didn't put that plot here. But it's beautiful. It picks out very nicely what happens. And we calculated alpha, and I don't know how I screwed up, but it looks like I screwed up because I wanted to show you alpha as a function of ATP concentration, because it's not at all linear. There is a low ATP behavior, and then there's a high ATP behavior, and then it flattens out at very high ATP. So it's a completely non-monotonic function of ATP concentration. And when you put ATP and motor concentration together, all hell breaks loose, because the motor concentration controls the ATP concentration behavior, the ATP concentration controls the motor concentration behavior, etc. So there's all kinds of fun there. But I apparently have screwed up, or I decided that you don't want to know all of these things. I can't remember which. So I'm just going to keep going with the slides. If you ask me again at the end, maybe I can pull it up from somewhere else. But this paper has been written. So this paper is in PRL 2023. The first author is Joshi. And it has all of the usual suspects, Baskaran, Hagen, Dojic. I can't remember who else. Lots of people. This is in 2023 PRL. Okay. Now, as I said before, what I want to do is I want to be able to spatiotemporally control stress. So what I have figured out is what is alpha as a function of ATP concentration and motor concentration and things like that. Now I want to make alpha spatially inhomogeneous. I want to make alpha large in some region of space and alpha small in some other region of space. What we are trying to do, and that has not worked yet, is to find some internal way where we can set a chemical gradient in something else so that we can control the alpha. That is not working yet. But what the experimentalists did in the meantime was they made a light-activated motor protein. So there are all kinds of proteins in nature that respond to light, that have conformational changes in the presence or absence of light. That's how plants are able to bend towards light and things like that. So that protein domain in plants is called eyelid. So what they did was they took the eyelid domain from the plant and attached it to the kinesin. So now we have kinesin that turns on when there is light and turns off when there is no light. So we can use blue light to control motor activity. Okay? So just as a proof of principle, a couple of movies. In the first movie, is it playing? Can you see it? The first movie, the light is turning on and off homogeneously. Everywhere the light is uniform, but it's turning on and off. And as you can see, it starts and stops, right? And now we've characterized the starting, stopping behavior, and we understand how the alpha changes with the start, stop of light, how much lag there is and things like that. And you can also do this other thing, which, did it play? Where you're shining light in one region of space, and activity only happens over there, and you drag that region of light around. Whatever you constructed, the aster you constructed follows you. So you can control light in space and time and change the activity in my system. So this is proof of principle. I don't have data yet because it's not clean, but we are working on taking experimental data, use machine learning Cindy to figure out the shined light intensity to alpha as a function of time. And there's actually a little lag here. Whenever there is a sharp change in intensity, the change in alpha is non-local in time. So we're still trying to sort that out. I don't have clean data on that yet, but we're working on it. But in the meantime, there's a bunch of theory that needs to be done. Supposing I could figure out how to control alpha as a function of space and time, I need to figure out what patterns of alpha will give me what behavior, right? And again, I don't want to guess. I don't want to put uniform intensity here, zero intensity here, spend all my time characterizing the transitional velocity. I'm doing all of these things, but that's not what will work for this project. Where, let's say I have high alpha here and zero alpha there. You look at the interfacial region, there will still be flows, and you can characterize those flows and try to understand what light gradients actually mean and things like that. That would be the physics approach. But if you take a data approach, what you do is, I want to find alpha of r comma t such that I can drive the system to any dynamical state of my choosing. I want to formulate it as broadly as possible. And it turns out we can. And the language is actually very old. The first attempt at doing this with this language is called optimal control theory. And optimal control theory goes way back. The first optimal controller that was built was by James Watts, the guy who built the first steam engine. This is called a centrifugal governor, and this is the object that controls the speed of an engine. And what basically happens here is that steam comes out of this thing and rotates the engine. The engine speed controls the angular velocity of this disk. The angular velocity of this disk controls the separation of these two masses. And the separation of these two masses controls this lever arm. So you can, if these two masses come closer together because the engine speed dropped, this lever arm will open more steam will come out. And if this spins fast and these balls separate, the arm will lower and the steam will reduce. So this is the idea of an optimal control loop, where you're trying to figure out how to get the system to be where you want it to be. So the mathematics of optimal control looks as follows. I'm going to formulate it in our physics language. The optimal control people use a different language. If you want to learn, and it's very powerful, the optimal control people use, it's spectacular. The book that I would recommend if you wanted to get your fingers into optimal control because it's very pretty is Brandeis. He wrote a data science for physicists and engineers book. It's awesome. That's where I learned optimal control from. It was awesome. So this is like I pushed you guys on the deep end of the pool. This is me voluntarily jumping into the deep end of the pool of something that I don't know how to do at all. Okay? So this is what we try to do. So let's say this is my problem. I have two equations, one for Q and one for U, that I'm giving it a representation like this. And what I want to do is I want to solve for alpha of r comma t in the time range 0 to some final time tf, given the initial state of my system and the final state of my system. That's the math problem I want to solve. Alpha is now function of space and time, and Q and U obey this equation. But instead of prescribing initial condition for Q and solving for Q and U at later times, which is what physicists would do, instead you say, now I'm going to give you boundary values in time. Not only am I telling you the initial value, I'm also telling you the final value. But now you have to solve for this field alpha such that this solution comes about. Okay? So there are existence questions that one can ask. These existence questions fall under the concepts of controllability and reachability. There is a whole lot of math here, and is it in principle possible is a question you can ask. And the answer is, for the fully nonlinear system, I have no idea. I don't know if it in principle exists or not, and mathematicians don't have techniques to prove this either. But for the linearized system, you can prove it. And we have proved it for the toner 2 and the active pneumatics and things like that. Optimal, it's controllable.
Solution unique?
I don't know about uniqueness. Because uniqueness is a very hard problem that I don't know how to solve. That's not enough math. Right? Controllability is easy. I have to prove some eigenvalue properties. No, uniqueness is too much math. Okay. But in practice, you don't have to prove controllability, you don't have to prove reachability, you don't have to do anything. You can just use optimal control without understanding the math at all in the following way. This is the physicist's approach. Proof of the pudding is in the eating of it. If it works, then it works. That's all I care. Right? So the way that you do it is you write down a cost function. You write a cost function which is minimum when my flow is in my target state, my Q is in my target state, and I also penalize alpha around some mean value because I'm looking for an experimental implementation and I know the range over which I will be able to vary alpha in my experiment. Okay? So I limit the variation in alpha about that range. And I also penalize gradients because I know that my digital light projector has pixel resolution. That's the best gradient I can get in my experiment. So I have to penalize gradients appropriately so that whatever solution I get here, I can actually implement in my experiment. Okay. And then you write down an action. This is very, very physicsy approach. The action just has the cost function that you wrote down, that you want to drive your system down, and you put it as Lagrange multipliers the dynamics of your system. That's all the action is. You introduce conjugate variables exactly like classical mechanics. Just write down the action, introduce conjugate variables, enforce the dynamics using Lagrange multipliers. So what you get is an Euler-Lagrange action. Once you get an Euler-Lagrange action, we are physicists. We can solve this in our sleep. Right? So I can derive the equations. I can't actually solve the equations in my sleep because they are very complicated. There's a huge mess of equations that are very expensive to solve if you try to solve them in some simple-minded scheme that I would use for forward problems. So there is a scheme that these people have figured out that's called the direct adjoint looping scheme, which is an iterative scheme for solving Euler-Lagrange problems such as this. Okay, so you borrow that iterative scheme from them and solve your equations. Okay? Okay, so that's the thing. What can you get out of something like this? You can get things like this. So this is my chaotic pneumatic doing its own thing. I want to find some particular light pattern that I will shine on this system. so that I get some pretty states. I want to get flat nematic. I want a nematic that stays flat. I want to shine light pattern on my nematic such that it stays flat. It becomes flat and stays flat. Or I want to produce coherent flows in my system. So this paper should appear on archive as soon as I go home, probably, because it's nominally done. I don't know why it's not posted yet. So, and it's fun, but I'll just show you one result from that paper. This was for coherent flow. Focus on the middle panel here and the bottom panel. The bottom panel is the light pattern, and the middle panel is the flow. Okay, that's what you're visualizing. Whenever you see yellow, that's high flow. Whenever you see black or blue, that's low flow. Whenever you see bright yellow, that's high activity. Whenever you see some teeny tiny bluish thing, that's low activity. And what I told my optimal control solver to do was to keep high flow here, and I don't care what it does anywhere else. That's what I told it. Okay, I want it to have high flow so that if I put a particle here, it ends up here, so that I can direct particles in my active fluid. So I want high flow here, and I don't care what happens elsewhere. So that's what the goal was. And what it did, if the movie plays, is give it a minute. This initial state is spurious. It won't stay there for very long. Eventually, it'll get to the state there where it can stay for very long, which is that guy. Can I pause it? Oh, it stopped at the right place. Good. So now, we have large flow here. We have some vortex structures outside. And this thing went away. Wait. I wanted to show the act. One moment. Sorry, I want to make a point with this movie. Once it gets to steady state, what I want you to notice in the light pattern thing is that there is almost no light where I want the flow. The light is all outside. Do you see what I'm saying? The region where I have coherent flow is not where I should shine the light. I should shine the light elsewhere. Yes, Danilo.
I just want to understand what time is here. You are solving an optimization problem, right?
Yeah.
You have a cost function. You came out.
You're asking how many iterations it took?
No. I mean, these are iterations.
No, these are not iterations. This is the final solution.
But what are the frames? What are the frames in
okay,
the
so the
animation?
frames here, I don't remember what frame rate my student made this movie in, but the solver, we typically save on the time scale of 1/10 alpha. So 1/alpha is my characteristic time scale. That's the time it takes for my defect to move a reasonable distance in my system, right? I take 1/10 of that time and save alpha values. And then just use that alpha to run a forward simulation to see what happens.
Okay, got it. Okay.
This is just a forward simulation. I found the
It's
alpha
a
from
forward simulation.
Yes.
It doesn't have to do. Okay.
Yeah, there are no movies of the optimal controller doing its crap.
Okay, that's what I got confused.
Yeah, absolutely.
Thank you.
We made a few movies just to test what it was doing and understand what it was doing, but it's completely worthless to show. So the final answers are all forward movies with the solution produced by the optimal controller. And what is happening in this thing when it's shining light on the outside rather than on the inside is it's setting up counter-rotating vortices on either side of the region where I want coherent flow. That's the solution the optimal controller found. It found a solution where you don't light the system at all in the middle of the channel. You light it outside and set up counter-rotating vortices with your light pattern so that you get a coherent flow in the middle. I showed this example because this makes physical sense as a choice for light pattern that one would use, right? So I like this example. Okay, so that's all the math. That's all the data-driven stuff. Now for the next 20 minutes or so, I'm just going to show you movies to see what else is happening and what other games we are playing with these kinds of approaches. Okay? I don't have enough data to implement any of these approaches for the systems that I'm showing you. There, I'm still playing baby physics questions before I can use all of this fancy data-driven stuff. So another system that we are playing with is this one. What this system is there is an actin network inside which these microtubules are intercalated. So the microtubules extending are pushing the actin network. And depending on the concentration of actin, you get something that looks very much like a dilute microtubule suspension. to something that looks like microphase separation with asters that are organizing the material into finite-sized objects, to global contraction, where the whole thing just contracts as one network. And this behavior just changes as a function of actin concentration. These experimental results have been published. The theory for this part of it should be showing up shortly. This is boring. This, I don't know what's happening. So this is part of the puzzles that are being played with right now. Okay, then one more. Oh, this is not going to be an hour-and-a-half talk. It's okay. This is the system that I'm currently writing up, where you have this microtubule stuff in here. The blacks, this is a liquid-liquid phase-separated domain. Inside is dextran, outside is PEG, and the microtubules like to sit in dextran. So they phase separate into this system, and it does this jiggling thing. Okay? And we're trying to figure out what this jiggling thing is, and it has lots of cute features. Do you remember Julia showed you an experiment with the bacteria where she saw this? Right? And the feature that is very important to understand this kind of fluctuation is the curvature is always sharper into the active fluid, and the curvature is always shallower out of the active fluid. And this asymmetry turns out to be characteristic of the active fluid. It's a property of the active fluid that you can figure out by just taking the active fluid equations and putting the boundary condition on it. Okay? And then you can rectify this. So one of my students built, so what we've done with this system, I mean, we haven't done it yet, but we are hoping to do it, is we built a reinforcement learning to figure out the light pattern, no optimal control, nothing, just blind reinforcement learning to figure out the light pattern so that I can augment these guys and push these guys so that I can get a pattern of curvature that I like in my system by playing with light activated motors. The reinforcement learning is working, but we haven't tested it yet in the experiment. There was a question behind you also? Yes.
Yes. Do you know why there's no merging or?
Oh, if you wait long
pin?
enough, it'll merge.
But yes.
Yeah. So
but they are quite approach at some moment, but they don't merge. And there's no pinning as well.
Say again.
There's no breaking out of the droplet.
Oh yes. If I increase the activity, there will be pinch off.
Okay.
Yeah, if I increase, so Zwanimir has a paper in which he has done exactly this, and where he can see pinch off, and the pinch off always happens this way. You get a droplet of the passive thing inside the active thing rather than the other way. So there are some various peculiarities to it. This was fine-tuned in PEG dextran concentration so that I could get isolated drops that lived for long periods of time so that we could play this game. There is no generic case. It depends on PEG dextran concentration, and you know the PEG dextran coarsening timescale. That coarsening timescale is affected by activity, which we are also sorting out. I don't exactly know how, but we're sorting that out now. But this was, just do this till you get, figure out what concentration in which you can get dilute droplets. So some graduate student ruined 3 months of their life to find the parameter region. Yes, there was another question? No? Okay. Okay. So this is really cool. So this active interfaces, I guarantee you, everybody is thinking of active interfaces. In every problem that, experimental problems that people are worrying about, they are worrying about active interfaces. There's activity on one side and not on the other side, and you're trying to figure out what that means for the interface. So this is a cool thing. And then there's one more. This I call the Godzilla movie. Wait for a minute. This, I don't know what's happening here. This is just a movie. The postdoc who produced this movie has not been able to reproduce it, so I don't know what's happening here. There is some elastic sheet, and that elastic sheet is modulated by the active fluid. The elastic sheet is just actin. There is no activity there. All of that Godzilla shaking business is coming from the microtubule that's there in the background. I don't know what it's doing. And then the elastic sheet is falling apart and stuff like that. We have no clue, right? So this is a movie that we put aside because it's too complicated. There are too many things happening there. So we just left the movie. We just show it in talks and say we don't know what we are doing. Yes?
So now I can ask the question. Microtubules work on actin?
No. Microtubule bundles are doing their own thing. They are aggregating by themselves. The actin is being pushed by the fluid, or if it comes into contact with a pushing microtubule, that will push the actin. The actin is completely passive.
Okay, because I was going to ask in the previous experiments
Uh-huh.
if you could reproduce what you showed yesterday. So have a low density of microtubules that accumulate in the preferred curvature regions of the
Yeah,
fluid.
so you can't do it with actin because actin is too floppy and get pushed around. So we've been trying to do that with GUVs. So unilamellar vesicles that are floppy enough and the microtubules does push on it, but there's a problem. The GUV stiffness is such that it starts fingering. It starts sticking in one corner and it starts accumulating membrane and it starts fingering. So I can't get it to be like nice and curved and well behaved. It becomes a mess very quickly. So I don't have we haven't figured out how to do that yet. Okay, so this is my Godzilla movie. Then other things. These are some other systems that are working in the lab. I'll tell you a little bit about each of these systems, and you should be seeing some papers with experiment and theory on these things, and a theory paper on this in the next few weeks. Let me tell you what's happening here. What's happening here is it's actually just microtubules and kinesin, but you change the kinesin, okay? You start with the same microtubule, but instead of the kinesin that we were using before, this is kinesin 4. This is a different kinesin. And what this kinesin does is it walks on the microtubule the same as the other kinesin, but once it gets to the end, it just stays there. It end accumulates on the microtubules, okay? So what I end up getting is initially this behaves exactly like the microtubule kinesin fluids that we've been using for many years now, but if you wait for a little while, what it does is all the kinesin ends up accumulating at the ends of these microtubules, then these guys self-assemble into a membrane. So you get an active membrane of these microtubules, which have these end accumulated kinesin. And when I'm drawing a cartoon like this, these are not just sticky rods with end sticking. These motors are actively being recruited from the fluid so as to keep a steady state here, and the microtubules are getting constantly recruited from the fluid, and then they fall off here and stuff like that. It's a dynamical membrane, okay? And what you're seeing in this movie is that membrane forming some fractal structure. The red things are the microtubule, and the blue things are the kinesin 4. It's just a lot of this membrane going around like this in this system. Yeah, so I have no idea how to study this, but what we have tried to do now is just take one segment like this and look at its dynamics of recruitment and leaving and build a model that will tell me what should be the effective bending modulus of this membrane should be. And then use that to see if we can understand something about this big messy system. I don't know, early days. 3D, this is 3D active nematics. This is the case where you put the microtubules together with FD viruses. So FD viruses are about 100 nanometers long. The microtubule is 1 micron long. So you have tiny FD viruses and these microtubules which form big bundles. You put equal concentrations of microtubules and FD viruses in the cup, and it'll do 3D active nematic stuff. Julia showed one movie from this data set, which was the disclination lines movie that was in the original paper. But we understand a lot more about 3D active nematics and disclinations, and at least theoretically. Experimentally, I don't know what to do with the light sheet data. The problem with this 3D active nematic with the data is I don't know how to do machine learning flow in 3D yet. What I have is I have light sheet data. The light sheet data has some frame rate, and you're tracking some beads and things like that in 3D. I don't know how to structure the data so that the machine can figure out that I'm giving it flow that is going up and down and this way and that way and so on. So there's a data problem there that I don't know how to crack. I probably need help from somebody who actually knows something about data. And this is the simple version of the Godzilla movie. I hope it plays again. So what you have is a 2D membrane of actin, and there is microtubule fluid all around it, on top, below it, on the sides, and so on. And the microtubule fluid shears this actin film, actin sheet. And we understand this somewhat now. We have written down a viscoelastic model for the actin sheet and coupled it to the active fluid, and it turns out that you can get this self-shearing mode under some circumstances, and that's what this is doing. But again, we have a data problem. We don't know how to extract from this the right data so I can test whether my theory is any good or anything like that. So that's still, I don't know what I'm doing. Okay, these are all the problems in my life. I'm telling you what are all the problems that are waiting for me once I go back home. Okay, all the fun with non-equilibrium StatMech ends now. I have to go back and look at all this crap. Okay, now last thing, I want to zoom way out. So the future of active matter in some very narrow microtubule, motor protein, cytoskeleton, let's make self-pumping fluids kind of thing is what I tried to tell you. I showed you all raw data of things I don't understand at all, that we have not published at all. This is just preview, so that you guys can start working out the theory and tell me, so that I figure out how to use these things. But if you zoom way out, and if you stick to this picture that I have, that I want to make myself a bag of crap that will do what I want it to do, we are at the right stage in human evolution to be able to do this. What do I mean by that? We have lots of tools that are coming online, and we have exciting times in the future. The first tool that is becoming very, very powerful at this point is synthetic biology. Synthetic biology is the art of implementing some particular biochemical cycle inside a bacterium. Okay, so you use CRISPR or whatever, cut out regions of the genome, add the genes you want for the particular proteins you want it to produce, and the rest is taken care of by chemistry. You can produce particular biochemical cycles. You can basically design the biochemical cycle you want, and some synthetic biologist will give you the DNA that you need to make that work. That's awesome, right? So make friends with synthetic biologists. De novo protein design. This is also awesome. So far we've been limited. So I have all this imagination, right? I want a motor that will do this. And we've tried, because there are various this chiral things with rods will do cool things. I know from theory, right? So I want one of those motors so that I can make something fun, right? But whenever we tried one of these rotary motors that was actually there in nature, either the biology doesn't work, or the physics doesn't work, or it falls apart, or something or the other goes wrong, okay? But de novo protein design is a technique where you basically take the 22 amino acids. See, the magic is that all of us, in spite of our complicated internal lives and things like that, are just a bag of 22 amino acids, 5 nucleic acids, some salt, some sugar, and some water, and some fat. That's all. As matter, that's all you are, right? So you take the 22 amino acids and start arranging them however you like, so that you can make structures that get you closer to what goal you are trying to accomplish, right? So Seth, one of the people in our gang of 4, has now learned how to do de novo protein design, and he's making our first protein, which we designed for our purposes. We wanted the protein to do what we wanted to do. I will tell you whether it did or not after we make the protein. We haven't managed to do that yet. So de novo protein design is another cool thing that you can play with, and there's lots of progress. I mean, if you just look at the people in California producing protein designs every day, this is huge. So you just follow the literature, there is so much you can borrow. Steal, we don't have to learn all this stuff, just steal. Use AlphaFold, steal from the California people, you can make your bespoke protein. And finally, our core interests, our meaning active matter people, which is mechanics and energetics. Identify the organization principles in space and time of all this crap that they will produce. We will never deal with this. Somebody will produce it and give us movies, right? And we need to figure out the mechanics and energetics of what's happening. So far, active matter has exclusively focused on the mechanics, right? We always assume the system is overdamped, and we don't care about energy, and we just figure out the mechanics, force balance. We have been in the Newton's third law regime. But we are limited by what we can use our knowledge for till we crack the energetics. So this is very baby stages. We started a program where we're trying to understand energetics. I'm going to the cellular energetics literature and look at the loop, because this is again magical. Think about what's happening. You take a cell, okay? These are experiments that people have done. They take a mouse oocyte or something like that, and they do calorimetry on the cell. Okay, there's a cell, it's in steady state, and you do calorimetry on the cell. What you find is that there is some food going in and some waste coming out. If you look at the chemical energy required change from the food to the waste, and you ask, okay, how much heat does that chemical energy correspond to? And measure with a calorimeter the heat produced by the cell, they are exactly equal. What does that mean? The cell is acting like an enzyme. It's just taking the food and converting it into waste and apparently doing nothing in energy space. But in function space and in mechanics space, it's doing all kinds of crap. How is that happening? How does this zero energy problem where everything dissipates into heat somehow manages to do stuff inside it? This is like really puzzling question that nobody knows the answer to, and everybody's beginning to play games. So we have to use tools of stochastic thermodynamics, we have to use tools of non-equilibrium statistical mechanics, and we need to make friends with the people who know their chemistry so that we can try to understand these energetics. So energetics is something that we really need to understand if we want to harness these things to actually make stuff out of it. Okay, and of course there is all kinds of magic happening in biochemistry, cell biology, and organismal biology, where people are identifying more and more proteins and identifying more and more pathways, and we have lots of information there. Though my problem with this information space is that I don't understand the papers. They are quite overwhelming. The language is different and so on. So I don't really read much. I go and find a biologist I like and ask them to explain it to me. So I don't know much about these things. These things I'm reading and learning, but these things are too hard. And in the middle of all of this, machine learning and data science. Machine learning and data science is what is going to help us crack this mess that biology is. Okay? And just to inspire you to take machine learning seriously, I mean, we physicists look down at machine learning. I look down at machine learning. It doesn't give me any understanding. What is the value of me feeding data and it knowing what is happening? I don't know what is happening. What is the use of this? That is my attitude towards machine learning. But now I think that we, the StatMech people, have to take machine learning seriously. And we have to take machine learning seriously for two reasons. One is we are the only people who will get us from AI to XAI. We are the only people who can work with machine learning and recognize features as emergent variables and look at the dynamics of features and understand what the model learned. Okay, there's a lot of effort in this direction. If you want to know more about the statistical mechanics of machine learning in this language, I recommend the papers of Surya Ganguly from Stanford. He's written a couple of reviews. He's written a whole lot of papers. It's really nice. Okay, so that's at the AI end of things. The other end is you can understand better how you function. The way that I want to make that point is to show you a movie. I apologize, I couldn't find a way to download or embed this movie. What this movie is showing is there is a person looking at this image, okay? And this white dot is moving according to the saccades of their eye. So they're watching the hole through which light goes into your eye, and that's this white hole. And at any given time, this is all you're actually seeing. This is all the light you're seeing. If you were actually seeing with your eye, this is all you will be able to see, this. But you're not seeing with your eye, you're seeing with your brain. It does the interpolation to produce this. So you think you're seeing this. So this whole approach of predictive probabilistic learning is going to be very useful for us to crack the problem of how do I go from this information to this information being steady in my awareness, right? So there's all kinds of cool stuff. So these people, these neuroscience people, are doing a lot of cool stuff with machine learning. Once you learn the language, it is not your field, but you can read all of those papers and they are lots of fun. I'm giving you recommendations for how to have fun, okay? All right. That's pretty much all I prepared, so I will stop here and take any further questions.
Thank you, Aparna. So let's have some questions. I have a question on
Yes,
your
Francesca.
Godzilla problem.
Which problem?
The Godzilla problem?
Godzilla problem, yes.
Yes. So if you go back to the movie,
Yes.
I was wondering if in that case, so the green stuff is above the suspension?
This image is in one plane. So it's a microscope. The depth of the sample is about 100 microns. And the actin is sitting in the middle. And there is microtubule on both sides. But what you're seeing is just the imaging plane.
Okay.
So this is all in one plane. So they put the focus of the microscope where the actin film is, and you're seeing whatever you can see in that plane. So some of it might be below, some of it might be above, but the imaging plane is on the actin.
So this is like maybe we are seeing like the active turbulence. Like
The active turbulence is
driven-
happening in the pink stuff.
Yes.
So do you see the magenta stuff?
Mhm.
That's just active turbulence.
Yeah.
Okay, that active turbulence is driving that Godzilla.
Is driving, yes.
Yes, the green Godzilla is being driven by the active turbulence.
So this is something like maybe it's an example of what Ricard Alert found in his paper, like when they have also like this kind of suspension, and they observed that there was kind of a flow exerted by this.
You're thinking of the Mixo papers?
Yes.
Yeah, no, what's happening in the Mixo is different.
Okay.
Yeah, because in the Mixo, the activity is only from the Mixo,
Yes.
and the buckling and all of that drama is also happening in Mixo.
I
The
see.
water is passive and is actually pressure controlled with a pump that controls the amount of water in agar. So the mechanism is actually rather different
Okay.
in that
see.
case. I think we're thinking of the same paper. Think of the Mixo paper, right?
Yes.
Yes, yeah,
Okay. Thank you, Aparna.
yes,
So in your light-activated fluid,
yes.
what do you think would happen if you placed an object like a passive particle that emitted light? The particle
And thereby
itself.
recruited these people. I think it'll be really cool. Instead of us shining from a digital light projector, if I could put a fluorophore or something inside it that activated the motors, I think that'll be really cool. Yeah, there are some chemistry problems that need to be addressed to find the correct light thing that the biochemistry will like, and the microtubule will not become unhappy and stuff like that. It's not a problem that anybody is working on right now, but I think that will be really cool. Right now, we're just hacking it. We just use a digital light projector to make the light. But eventually, yes. Few years from now, yes.
Just a short question. What's the difference between the top interface and the bottom interface of your
There should be no difference,
Right.
though in this movie, there are not that many microtubules in the
On the
focal
other side.
plane on top, but you can see them better in the bottom. Nominally, there should be no difference. We don't have confocal for the Godzilla, but we have confocal for the better controlled experiments, which are repeatable. And then you can see that the microtubule is in the bottom, microtubule is at the top, and the actin is just sitting in the middle and doing its thing. Okay? This Godzilla movie is just for fun. This never came back again. Yes.
Maybe I lost it, but when you show this machine learning reconstruction of the mesoscopic equation terms, these were real data.
Yes.
So the question is, so you claim that it captured perfectly all the symmetry you expect
yes.
and nothing else.
And the active stress term, that's all. And it gave
Yeah.
one extra term which had a grad rho. It was a pressure-like term that showed up in the flow equation, but it's not super important. It has quite a small coefficient.
Okay. And have you tried to test it on synthetic data?
Oh, yes. The
With
first time
with
I
a lot-
wa-
with increasing noise, increasing
Yes,
noise,
yes,
et cetera?
absolutely, absolutely. It's in the paper that we wrote. Yes, absolutely. We just took numerical
Actually, I
solutions
did that.
and ramped up the noise because we had to find the effect of the Gaussian blur. We have to put Gaussian blur on the data because we are taking derivatives on the data, right?
Yeah.
So we wanted to understand if we are losing something by putting Gaussian blurs on the data. That we did with the synthetic data. Just solve the hydrodynamic equations. So yes, we did test that.
And it works very
It
well.
works okay.
Okay, thank
I mean, it works okay to some extent. If you blur beyond a point, you lose everything. Absolutely. It works okay. So it gives you a rule of thumb as to how much you can blur without losing information.
Thanks.
Okay, so apparently we don't have more questions, so let's thank Aparna again
Yes,
for
thank
these
you.
amazing lectures.